This example involves harmonic motion. So here's the illustration. You have a spring here, and at the bottom of the spring there is some kind of weight. Okay. So let's say W right here. And let's say this is the steady state or equilibrium position right there. So right there will be Y equals 0. And what happens if you pull or push on this spring? Remember, this is nothing moving right there. And then this will go up and down, right? And so now you have a bouncing. It will go, if you pull it, it will go up. If you push it, it will go down. But then it bounces back, and you have a motion here. So this is Y of t. You have the position Y is now a function of time. Okay? And let's say that in this case, what's given to us is that Y of t is the following trig function 4 cosine t. This is a very simplified function because in reality, if you go back to trig, you have some 2 pi t over something. You have the period right there, or the frequency, if you remember. But this is not a course in trig, so I'm not going to discuss it right now. But in physics, you're probably going to learn that again. What we need to do, we need to find the velocity. And the velocity will be v of t. And the acceleration. A of t. Now the solution itself is very simple. The velocity is the first derivative, the acceleration is the second derivative, so v of t will be y prime, the first derivative, and the derivative of the cosine is negative sine, so we'll have negative 4 sine of t. Okay. What about the acceleration? Well, the acceleration is the derivative of the velocity or the second derivative of the position, right? We wrote it like this. So now we need to take the derivative of sine of t. Well, the derivative of sine of t is cosine t, so we end up having negative 4 cosine t. One thing to notice that, and this is an important observation, take you to differential equation. We have a basic differential equation here. If you look carefully, notice that y prime equals negative 4 cosine t is simply negative y, because y is 4 cosine t, right? So the acceleration is the negative of the position. And this is typical to harmonic motion. When you have harmonic motion, something bouncing like that, then the acceleration is always the negative of the function, the original function. JT, hang on to your question. One more thing that I need to write, okay? So here's what we have. We have y prime equals negative y, or we can write it as, y double prime. Y double prime, and this is a function of the time, y double prime of t, plus y of t equals 0. And this is a basic differential equation. Differential equation of where you have a function and its derivative in the same statement, the same equation. So the note here, this is an example of a differential equation. Now, why I point this out? Because most things that have to do with motion or with dynamic, moving object, and all of that can be described using differential equations. JT, your question, and then Jason.
Why would you treat 4 cosine t like the product
I did not. 4 is a constant. I use constant multiplier. You can ignore the 4. What is the derivative of the cosine? Well, it's the negative sign. What is the derivative of the sine? Is I'm sorry, what is the derivative of cosine is the sine, the derivative of sine is the cosine. The negative 4 is just a constant multiplier. So did not use the product rule.
So for problems with motion, would this always be the same as in the function of the second derivative equal the function of the first function but inverse?
If it is a harmonic motion, yes. If it's a spring or something harmonic, like you're looking at grandfather clock, the pendulum. That would be also, that's an harmonic motion. So this is typical for this type of motion.